quickly review where we started as of the last two classes, and then just we'll proceed on what we have for today. As you remember, we were using the second chapter of the book that I shared you, and this chapter has got end-to-end machine learning project, which I believed would help us to go over the foundations of machine learning. It has got almost every steps that you would need for training a machine learning model. So it starts with checking the Google Colab. Now, this is a Jupyter notebook that we are hosting on a Google Colab. And I shared, again, I would say I shared this notebook 2 weeks ago, and you can find it right here under my share, and then in the Google, in the foundations of machine learning, and then notebooks. So in the notebooks, we have this notebook, right? And the other notebook that we used in the past was Introduction to NumPy, Pandas, and Matplotlib. These are the three packages that we are using even in the current end-to-end machine learning. Also, there are more packages that we have been importing. In any case, so you can find a notebook right here. So this notebook is an end-to-end machine learning notebook that basically goes from importing the data all the way to transforming it and then just creating different machine learning models that enables us to get insights about the data or help us predict what we can see in the future based on the given data. The data that we're using is the California housing data, a housing data set, and then just the source is here. You can find the data from here, and then we are importing it and looking at the detail of the data. The data has got about 20,640 rows with 10 columns or 10 features. And that's what we're using. And the data dictionary of this data looks like this. Each column, the longitude, latitude, housing median, age, the total rooms, the total bedrooms. This is about the house and the population and the households in each house, and the median income of the house, the median house value, the price of the house, and the proximity of the house to ocean, right? So these are the 10 attributes that we have. And we have been, accessing some of the details of the data, like, for example, the ocean proximity data, the distinct values for the housing proximity and the corresponding count of the data. As you can see here, this gives us like inland, near ocean, near bay, or island. So these are the total number of records in the housing data set with the corresponding ocean proximity. On the other hand, the population in the housing is also given as counts, and this many population and these 25 records, this many population, 24 records, this many population, 24 records, and it goes on like that. And as you can see, like just these are apartments. I believe these are some big apartments, it looks like. And these are individual houses. And the ocean proximity, I think this is a repetition. In any case, just furthermore, we can describe the house. This description means the statistical description of the house, the housing data set for each attribute, especially for each numeric attribute, we get the mean, standard deviation, the minimum, the 25s, the first quartile, the second, and the third quartile, and the maximum values of the data can be calculated just like this. And this is what we could do. And then we went on trying to save, create a storage location or like a folder location where we can save graphs that we generate from the data. And then just these are the different graphs that we generated. This is a set of histogram for each of the data set that we have. How do we know it is histogram? Because we said that here is a histogram, and the number of bins in each histogram is 50, and the size of each graph is like this. And the total number of, I mean, just each attribute is, plotted as a graph. Each attribute is plotted as a histogram, and we have 9 numeric attributes. 9 of them are plotted as histogram. And then we saw different approaches of creating a test set from a given data set. We can split a data set into training and testing data set. There are different approaches. Among the approaches are, we can write a custom code to split the data into test and training, or we can use existing method like train, test, split from a scalar model selection class from a scalar package. Then just we can say we can split the data using this method. Train, test, split, the housing, which is a data set, the test size 0.2 means to 20%, test size, and the remaining 80% is going to be for the training set. And the random set is equal to 42. This is a magic number that we usually use, which is believed to maintain the state of the internal data, so that just every repeated call can generate the same combinations, the same portions of training set and testing set. Although just the number remains the same, but we want to even the data inside the test split and the training split are somehow identical. And as you can see, the number of records in the test set is 4,128, and the number of records in the training set is the remaining out of the 20,000 plus records. Any other is that we saw where basically creating different types of graphs based on that. As you can see here, the income, the median income was being split into categorical data, and saying that just let's use 1, 2, 3, 4, 5 categories so that we can split the income data into 5 categories, and then this number of these categories were split, income category by the number of districts were categorized or plotted like this. You can use different types of techniques to observe different insights in your data set. And so this is pretty much about like just splitting the data into test and training. And there are this method also covered in detail in the first, I believe in the first partly, in the second again about splitting the data. Any other is visualizing the data in a geographic map. As you may remember, this looks like just a graph on a US map, and we also did that mapping on the actual map down somewhere down here. So on the actual mapping, so we used the California map, and then just using the housing price on California, we basically plotted this data on the California map. So this is another way of visualizing the diagram. And as you can see, the reddish parts are the median house value in USD is higher as the color becomes redder, right? As it becomes more red, and what that means is, like, if you see, like, just in the coastal areas, houses close to the beach are very expensive, right? The median price of the houses close to the beach are more red in color. So they are obviously, like, just in as I said last time, in US, if you have like just a house by a beach or like just with a water having a proximity to water, your house price is higher. Like just could be lake, viewing lake, water view adds much more value to your housing price. So this is what really reflects on the map. And the other thing is, we wanted to just another way of clarifying. I mean, clean data cleaning is making sure that multi-collinearity doesn't exist in your data set. So to ensure that multi-collinearity doesn't exist, you can use a correlation matrix of your data set, and then just you can only do correlation for numeric data attributes. And the numeric data attributes are out of 10, they are 9. We have all these 9 attributes, and then just the matrix is both the attributes are at the top and like just vertically, and then just each attribute on the vertical line gets correlated with the horizontal. And if you see like just a number close to, as you may remember from your statistics class, correlation values range between -1 and 1. -1 means a opposite correlation. +1 is a complete straight correlation. And then just 1 is an ideal correlation. As you can see on the diagonal, you see ones, 1 here, 1 here, and 1 here. And if you see the intersection, this one is for the attribute to itself, which means the attribute, if you take both values as the same attribute, it becomes 1. But if you see here, this value, the household correlation value, the total number of rooms, obviously, if you have so many rooms in your house, or the need for so many rooms would indicate the possibility of having more households. So just in most cases, people buy houses with this number of rooms that correspond to their household, right? So this is another indication. And the population also indicates, so just mainly correlation, when correlation gets close to 1, that means the two attributes are increasing in the same direction. As one attribute increases, the other also increases. If it is -1, as one attribute increases, the other decreases. So that helps to basically just remove unnecessary attributes from your model training process. You don't want an attribute represented by another attribute, or that representation is interpreted using correlation. If one attribute is strongly correlated with another attribute, or negatively strongly correlated with another attribute, you don't want both attributes to be in your training data set. So just for that, you would have to use this correlation matrix. And correlation matrix calculates the Pearson's coefficient of correlation between -1 and 1. As you can see, there is -1 here between latitude and longitude, and there are some negative values, as you can see here, and other negative values are here. So between -1 and 1 correlation, and ensure that your data set doesn't have a strongly negatively correlated or strongly positively correlated attributes together in your data set. You have to get rid of one of them so that you can have a proper model training. For that reason, we did this. And the other one is, just doing a graph using a scatter plot. That basically also gives you, how how the data is represented, and just the median house value with the median house value, as you can see, they are kind of opposite to each other, and you can basically see the graph and just the orientation of the growth between median income with median house value. So only selected values are taken, but just you can take all the attributes, especially the numeric attributes, and do a scatter graph to see another way of visualizing the correlation between just whether or not you can have, for example, here you can draw a line, right, like this. And what that means is the median house value, which is on the y-axis. What is the x-axis here? The median income. The median income and the median house value seems to have like a strong correlation. And the median house value and the median income, let's see their value. The median income is here. The median house value is somewhere at the end. The median house value. This is how you can see the 0.68, which is like the slope of their correlation, and more can be seen or visualized. And as you can see here, the median income with the median house value, just another way of looking at it. In any case, the graphs tell you some strong correlation between attributes, especially if you can draw a line on a dense part of a dense distribution of the scattered plot. You can do that. So these are some of the things that we saw last time, and just we started doing data cleaning, and today we will move on to data transformation and data transformation. And if I remember correct, we started about handling text and categorical attributes. When handling text and categorical values, one way to do is converting your data, especially just in categorical values. You can convert your data into ordinal values, ordered values, whereby just you can assign ordered numbers, 1, 2, 3. Ordinal means that. Or another approach is one-hot encoding, which means creating another transformation of data from a categorical or a non-numeric value to a numeric representation of it. And so just we can see this. I remember we covered it, but we can quickly see this. So this ordinal encoder, as you can see, encode categorical features as an integer array. The input of this transformer should be an array like of integers or strings, denoting the values taken on by categorical discrete features, and the features are covered to converted to ordinal integers, right? So just given values, given categorical or non-numeric values, we will get integer values, order number 1, 2, 3, 4, like that, integer numbers. And so as you can see here, for the housing categorical data, we can encode here ocean proximity was taken as housing cat. So this is what we have. the ocean proximity. Just we are taking only the ocean proximity column of the entire data set. And now looking at 8 of those values, let's make this 10 of the rows show us these 10 values. And the first one is nearby, the second one is less than 1 hour from ocean, or it is inland, near ocean, inland. It goes like this, right? So these values are categorical values for ocean proximity, and we wanted to change them to ordinal values or give them ordered values. Then you can have ordinal encoder, and then just and then the housing category cat encoded, which is this is our data set, the housing cat. Now we are encoding it, passing the housing cat, then just we do fit transform. Remember, ordinal encoder is another kind of small model. We are creating a small model right here that enables us to transform a column, a data, a column in the given data set. So fit usually comes with models. So fitting means converting or transforming. So then just we have this ordinal encoder initialized, and then we are converting it using this transformation model. Then now let me run this. Remember, this 8 was because of the yeah. So I think just we are converting the entire thing, but we are basically we are querying the entire categorical data of data for the ocean proximity, and we are simply just viewing only the top 10. And here we can see the top 15 if we want. Then just let me run first this. The transformation is done, and then just the top 15 records will be here. In the encoded, we have 3, 0, 1, 1, 4, 1, 0, 3, 0, 1, 0, 1, 0, 0, 1, 4. So for the 15 rows, the top rows, these are the values. 3 is assigned for near bay, and wherever near bay is, you will see 3. For example, I just for this one, let me make it equal so that we can properly map it, right? So for the 10 values, 3, and then just 3 from the bottom, we have 3, right? In 3 from the bottom, 3. Less than 1 hour, the next one is less than 1 hour ocean, which is assigned to 0. So we have 0 for this value, 0 for this value, 0, 0 for these values. So this is how we transform. The categorical values are transformed into numeric ordinal values. That's one way. Another way is transforming the data using one-hot encoder. One-hot encoder is a way to transform data into using the distinct values. The difference between ordinal encoder and one-hot encoder is that one-hot ordinal encoder transforms the data set into ordered numbers, but the one-hot encoding transforms the categorical value into a presence or absence of that particular categorical value in a cell, and it adds as many columns as we have unique values. For example, like here, we had how many unique values? As you can see from these numbers, we have 0, 1, although we don't have two in the list, the distinct values. Let's see. The distinct values, I think we presented the distinct values somewhere here. Okay. Okay, population, households, ocean proximity. Okay. I went further. Okay, let me take this. Let's try this. Okay. Jesus. Okay, so here we have basically just I'm not interested on the value count, but the distinct values. For the distinct values, we have 1, 2, 3, 4, and 5 values, right? So these are the 5 distinct values of the ocean proximity categorical values. Each of these categorical values have this many counts in the total number of rows. We are not interested in that, but what we are interested is to okay, it was actually right here. 1, 2, 3, 4, 5 values. And for these 5 values, we wanted to create a one-hot encoder. And just look at what happens here. One-hot encoder, we are encoding the housing categorical, the housing tab, which is this data set that we basically got here, that we were trying to encode, right? Which means only the column, we are only looking at the ocean proximity value. Now we are going to do a one-hot encoding of this data set. One-hot encoding of this data set, one column is going to generate multiple columns, five columns. And let's see what happens. And 1, 2, 3, 4, 5 columns, right? So this is how it becomes, and then we can have this and the housing. Let's see. Let's add one more. So because this is an array, we cannot display it. In any case, we are basically just looking at the top three and the bottom three values, and each zero represents the absence of the categorical value. And as you can see here, the categorical values are these ones and these ones. And this array is used as a column. This array is used as a column, and if you see here, this array in the first row, we have 0 for this, 0 for this, 0 for this, but nearby is 1, and 0 for near ocean. In the second row, less than 1 hour to ocean is 1, for the other 0, 0, 0, 0. So basically, like just what we are creating is horizontally a column for each unique value. One column, the second column, the third column, and the fourth, the fifth column. So these columns are being added onto the data set. Then what's going to happen is if the particular row has got that one value, one of these values, it is going to be set to 1, but 0 for the rest of the other values. So this is what one hot encoder is doing. As you can see here, categorical encoder categories are these, and then just let's do diff test, and we are creating these values. Ocean proximity to be inland and nearby. Then, so if you see here, the ocean proximity island and the ocean proximity nearby is going to be 1 for ocean proximity 1, and ocean proximity nearby is because the first one is inland, now it is inland, and nearby is another. So ocean proximity, part of the name of the column is going to be used from the column, the original column, and the remaining, the newly added column is going to be underscore whatever unique value that you have in the data set, underscore inland, and then underscore nearby. So the new data set will have this. Any other encoding is if we want DF test to be treated using the original encoder. This is the categorical encoder, right? So the categorical encoder is created here to encode. The categorical encoder is created here to encode our data set. And if we use the categorical encoder on this new data set, DF test only has got these two values, two rows, one having inland, or just to simply show this is after the transformation, but before the transformation, if it, let's see. Okay, this is overwriting it. Before overwriting, this is the ocean proximity is equal to inland and nearby. Get dummies is another way of one hot encoding approach. Get dummies is another way. In pandas data frame, we can have get dummies. Get dummies does the convert categorical values into a one hot encoding like attribute. So without doing this, for ocean proximity inland and nearby, the two rows, let's use the original encoder that we created up here. The original encoder that we created up here. Let me delete this one so that we can get easily to see. So the original encoder that we created here is the cat encoder using one-hot encoding, and then just we trained it using the housing categorical data set. Then just the cat encoder can be used. And cat encoder, when we use cat encoder for transforming, then transform here. Transform the cat encoder, which was trained using the 5 unique values, the 5 unique ocean proximity, but on a data set having this inland and nearby for these two rows, what would happen? And as you may remember, we had this, no, okay. Yes, so we have these orders. The categories were these. Okay, I don't have to write it. The categories are 1, 2, 3, 4, 5, but we only have inland and nearby. For this row, what happens is going to be the expectation is going to be the value for this one is going to be like this. Ocean is 0 because in inland is 1, and for the remaining is going to be 0. 3, 4, 5. And now here, what's going to happen is the other one is nearby. Nearby is the fourth. So 1, 2, 3, and the fourth is going to be 1, and the fifth is 0. So sorry, this is supposed to be 0. So this is what we expect after transformation, because the first row is inland, then it will look like this. The second one is nearby, it's going to be like this. So just let's run this. Right? When we run, the first, as you can see, the second at the top, and the fourth at the second row. So this is what is going to happen. What happened? So we have 5 columns that got created, and then we can have this using one-hot encoder. We can get the data transformed into just what we're trying to discuss right now is how we can transform our data into one-hot encoder using one-hot encoder. Basically, like just transformation has got different ways. We have different types of transformations, and some of these are transforming categorical data into numeric values. Categorical data, converting categorical data into numeric values can happen in 2 ways. One is using ordinal values, and second, using one-hot encoder. So these are the different approaches. And the other thing is that we can use is to handle unknown values. Whenever unknown value comes, usually like just in a given data, where in reality you will have a data set given to you, and especially like just when you are training a model, you know a certain reality at the point, just at the training time. During that training time, the reality that you get may be different from the actual reality in the future. In the future, you may have a categorical value that you never saw in your training data set, or when you were sampling data, sometimes you may have to sample your data to minimize the computational need. And when you do that, you may have ignored some important distinct categorical values during your sampling. So you can say that if after for your transformation, you can create like just one-hot encoder like this, and then any value that you don't know that you didn't represent during training, you can say ignore them. So this is what it means. Categorical encoder and ignore. As you can see here, less than 2 hours from ocean, this data value doesn't exist in the ocean proximity. In the ocean proximity, we only have these values, less than 1 hour from ocean, and then inland, island, nearby, near ocean. These are the 5 distinct values. Now, when we get these, then let's when we have these, then our data looks like this. All right, our data looks like this. Less than 2 hour ocean. If you see here, inland and then nearby, but here island. And do we have island? Yes, we have island, but less than 2 hour ocean we don't have. And how does our one hot encoding transformer handle? And if it has unknown value, then we ignore it. And then if we set this to ignore, then the first row for that corresponds to less than 2 hour will become all 0, because none of the values, known values, are being represented. So just all 0 is going to be set. But the second row, since island is part of the original value, 0, 1, 2, on the third values become 1. So this is how you would transform your categorical values into numeric. And the point here is ignoring a value that you don't know. And this can happen in reality. In reality, you would have to set this value to ignore, because or every value that you know or some values that you don't know may come as part of just a data set that you would have to predict using the model and things like that. And here, the categorical encoder feature names are ocean proximity. This is the only encoded value, because out of the 10 columns that we have on the housing dataset, only 1 column was categorical, which is the ocean proximity. And then the other thing is the ocean, the output of this feature name, the ocean for ocean proximity, we will get how many columns, additional columns. The new features that come out of this encoder are 1, 2, 3, 4, and 5. 5 outputs will come. 5 additional columns will come, which is equal to the number of distinct values. The number of distinct values in the ocean proximity were 5. Distinct value in the ocean proximity were 5. 1, 2, 3, 4, 5. For each value, we will get a corresponding column. But in each row, only one of these 5 values will be set to 1. The rest is going to be set to 0. This is how you transform a data into one hot encoder. A data into one hot encoder using one hot encoder. And when you do one hot encoding, then just you will get so many values, so many additional columns. And at times, one hot encoding is not advisable, because if you have so many distinct values, basically your data will be spread. Will have so many columns, having only one of the columns in the value set to 1, the rest 0, and the size of your data will be bigger because of the additional number of columns and so many zeros, but only one set to only one of the columns corresponding to that particular value in the row. And so just This being said, on categorical values, numeric values can also be transformed. Numeric values. At times, you may want to transform numeric values to scale them, to normalize the data, to basically properly represent, and even to fill missing values using non-statistical techniques. Among the transformation of numeric values is using minimum maximum scaling. The min max scalar is one way of transforming a numeric value. For example, so the min max scalar, as you can see, most of the data transformation approach, especially like just the ones that we already discussed, the ordinal encoder, the one hot encoder, now the min max scalar are in the scikit-learn pre-processing. Now just min max scalar, again, the standard scalar is inside in the pre-processing. If I scroll up, it's a little more. And search for these, you see, go up, data pre-processing. Ordinal encoder is from the data pre-processing, and going down. Do we have more up? Yeah. So function transformer, standard scalar are from. That's where we use them. Now, going back where we started, ordinal encoder. One encoder. Okay, min-max scalar. So we are here. Min-max scalar means scaling the value using the minimum and the maximum. Let's see. Let's run this. And the housing min-max scaled feature ranging from -1 to feature range is equal to -1 to 1, and then just the housing for min-max. Let's load the. So here is what it is. Transforms feature by scaling each feature to a given range. This estimator scales and translates each feature individually such that it is in the given range on the training set. Example, between 0 and 1. Now we are scaling it using min-max scalar to have each value between -1 and 1. Between -1 and 1. So the max minus the minimum. So this helps us to use a standard deviation based or X scaled based using the minimum and maximum values. So, for example, the housing numeric min-max scaled is initialized using min-max scaled fit transform the housing numeric values. Housing num contains only the numeric features, If you remember, I think just we got it somewhere up here. That is the feature scaling, and okay. Yeah, so here it is. The number type, the housing, select the data type, include number only. So this is what we are using. This data set is from the housing data set that contains all the data set, but selects only the numeric columns. the numeric columns. So okay, so the numeric columns. So now for all the numeric columns are going to be min max scaled. Let's do this. And min max scaled. So this is done. And let's see what it looks like. Head. Okay. So the min max scaled is, you see, negative 0.6, for example, for the first row, and then 0.11, the second column. So just all the first columns are like this, the second columns are like this, and the last columns. So it goes, the last column is like this. So the value is set between -1 and 1, between -1 and 1. So the closest to -1 is negative 0.99, and the closest to we don't have just a value close to 1, but we set the scaling to happen between -1 and 1. So every value is scaled down to -1 and 1 value. And again, a standard scaler is another scaling mechanism, which basically scales using a standard deviation. Using standard deviation. Standardized features by removing the mean and scaling to unit variance. The standard score of a sample X is calculated as Z is equal to X minus the unit divided by S, where U is the mean of the training sample or 0, and with mean is equal to 4, and S is a standard deviation of. So and X is the corresponding value. X is each value. U is the mean divided by standard deviation, which is the Z-score. So now we are using Z-score of every value. So when we run this, we get the Z-score value, and here is going to be the Z-score representation. There you go. So the Z-score of the first row, the first column is negative 1.4, etc. And so this is what the value looks like. So this is Z-scored transformation of the dataset. So you can transform the entire dataset. This is transforming the entire dataset. Fit, transform, fit, and then transform. So then you can again transform data using natural logarithm. For example, the population column is transformed using the natural logarithm. As you can see, this is a population, but this is a population before transformation. If you see here, this is simply just using the housing data set, and population column of it, the population column of the housing data set, and creating a histogram with 50 bins. So that is this one, this graph. Another graph, the second graph, is represented by this, the housing population, and then the apply in NumPy logarithm. This is transforming the population using natural logarithm. As you can see, log X, and this is the natural logarithm. Natural logarithm is the logarithm to base E. E is approximately equal to 2.7, an irrational number and then just is equal to 2.7, and that continues indefinitely. So So you can transform. So another way of transforming data. Remember the discussion that we had earlier. The first transformation, new for numeric values, is using min-max scalar, min-max, using the minimum and the maximum, and then we can scale the values between -1 and 1, between -1 and 1. The other scaling is using the z-score, z-score of each value, each numeric value. So this is the transformation about numeric value. Another transformation is using logarithmic transformation. We can apply natural logarithm on numeric values, and this is one way. And going more, we can discuss more on the possible transformation, values, and we can utilize different approaches. And another thing to deal with is using models like linear regressions or clustering techniques to fill missing data values. Let me stop before I proceed on this. Let me stop here and let you ask questions. Okay, so I see as binary categorical data have only two labels, yes or no, they can be labeled as 0 and 1 just by using ordinal encoding. So is it necessary to use one-hot encoding for binary categorical data? Can we include that one-hot encoding is suitable? Can we conclude that one-hot encoding is suitable just for categorical data with multiple categories greater or equal to 3 categories? Yes, you know, one thing that you should make sure is yes, for binary values, you can say 0 and 1, period. And one general thing, as you obviously know, that you should avoid is doing any numeric operations on converted categorical values. Categorical values get converted only if the algorithm that you are targeting to use requires numeric values. If the algorithm that you are targeting to use doesn't need categorical values, doesn't need categorical values to be converted to numeric values, then just you shouldn't mess with the numbers. Transformation is required only when you have to deal with algorithms or summarizations that require numeric representation of every data point or every attribute of your data point. And categorical values, one-hot encoding, for categorical values, you can choose between ordinal or one-hot encoding. And if there is a defined order, you can use ordinal values. If there is no defined order, you can use one-hot encoding. Both ordinal values, ordinal encoding and categorical encoding can be used. But if your encoding, I mean, if your dataset has got so many distinct values that would basically just expand your dataset horizontally, because one-hot encoding creates one column for every unique value. Let's say you have 200 unique values in a 10,000 records dataset. For 10,000 records of dataset, if you add 200 unique values, that means you are going to add 200 columns. So you don't have to do that. Instead, converting that to ordinal values saves space for you. So that's one thing that you would have to, strike the balance between the number of columns that you would get as a result of category one-hot encoding versus ordinal encoding. So that's what I can say. Although the answer is long, but you have to be very creative about and just mindful about the corresponding outcome of your decision. Is there any way to choose which encoding techniques is or are suitable for what kind of data and model? So like for each algorithm require this expectation about what they need. Some algorithms will take automatically just the categorical values as they are, right? Even some algorithms would require you to change your numeric values into categorical values. For example, a priori for classification, a priori algorithm requires you to change your categorical data, your numeric data into categories, right? Because it wants to deal with names, right? Name representations of your data. But some algorithms require all numeric values. So depending upon the definition and the requirement of your algorithm, you would have to make the right judgment. It's very difficult to answer this is suitable for this one because each algorithm has got its own requirement. I can't attend the class due to network problem. Okay, I will share the recording so you won't miss anything. I am unable to join the meeting. Link is not okay to my email. How to fix? Please work with your school coordinator on these areas, and then they can let me know if what issue you're running into. I cannot actively participate today as I am engaged overlapping events now. Sorry for. Okay, it's fine. I understand. Okay. No question, no further question other than this. Okay. 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 So, okay. So another transformation technique is using linear regression. It's interesting. Linear regression is one of the supervised machine learning model. One of the supervised, the simplest supervised machine learning model. And now, just as part of this process, you are also looking at a model, a machine learning model, one of the supervised machine learning model. And if I hover linear regression or ordinary least square linear regression fits a linear model with coefficient W is equal to W1 up to W2 to P to minimize the residual sum square between the observed targets in the dataset and the targets predicted by the linear approximation. We will discuss probably more about some of these algorithms, but just linear regression is an algorithm where you can, train to on a data set to fit your data set to fit and predict future values. And it only works on numeric values, only works on numeric values. And housing labels, let's see where we got this data set from. Okay. Sorry. Okay, linear regression. Okay. No, so just we needed this value where we got this from. Okay. 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 Housing labels is the training data set, the median house value seems to be the housing label that we have here. And okay. Things are getting slower on my side, so just bear with me. Okay. Bear with me. Things seem to be slower here. Okay, let's see what the housing label contains. This is what the housing label contains. Let me see it. Is okay. Anyways, so these are the values. This value, and just it only contains numeric values, and it contains numeric values. What it means is it has only one value that we wanted to predict. The reason why we need linear regression for one value is basically we wanted to predict whatever method that we have or to basically predict a missing value. Linear regression predicts a continuous value. And then if there is any missing value, then we can basically transform and just predict whatever missing value in that location. So the target scalar is a standard scalar, and we feed transform labels to data frame, and then we can have the model and the housing median income, and then just the scaled labels. The scaled labels, we are scaling the median, this value, because to frame is another requirement. We are basically converting the housing label to a frame, and then we are generating scaled labels from using the target scalar. The target scalar is a standard scalar. Standard scalar turns data into a z-square, as we saw earlier, z-square, which is equal to x minus the mean of the column divided by the standard deviation of that particular column. Then z is going to be the score. Now we are creating a model. This model is a linear transformation model, and then we are fitting the median income value of the data. And the scaled labels are again used the median income in the scaled labels. The scaled labels are the median, okay, the housing labels and the median house value are also no, hold on. That's no, sorry. So this is where it starts. The median value of the median house value of the training data set is the housing label, and then we are using that same label to create the model. Okay. Yeah, here it is. So, and then we have this, we are fitting, and then just we have this model trained on the scaled label value. And then just let's say we have some new data with the housing income and the scale prediction are going to be the new data, right? And then just using the model, we predict. And the predictions are generated as the using the target. The predictions will be set. Now the scaled predict. Oh, here is one important point here. This step predicts in the scaled size. And the next step inverses the original scale. Okay, now the prediction, whatever prediction that we get from for this new data, they say just these are five of the values, the last 5 values from the housing data set, and then just we are assuming that these are the new data. And if we see here, it may fail because yeah, so it's good. So the median income is going to be 2.0987, and the corresponding prediction you will see, and then just we will run this, and I will show you each value. And the prediction looks as follows. The scaled prediction. The scaled prediction is negative 0.6, but this is not our target value. The target, because the scaled prediction is a value that we get from a model that uses transformation. Remember, we were using scalar, like just standard scalar, and then this is using the standard scalar, this value. Now the actual prediction, as you can see here, we are inversing the transformation from target using the target scalar and then passing the scaled prediction. And here, the actual prediction value will be like this. You see the difference? Now these were the predicted values from just with the scaled prediction. and this is the actual value after inversing the prediction. So it's important in data transformation that you don't forget the type of transformations that you have used for your data transformation. Once you used a data transformation, don't forget the model that you used for the transformation, because later, at a later point, you will be using it to go back to your original. And the transformation, especially like this, the scale, the standard scalar, the min max scalar, have ways of getting. And the linear regression came here just to show the fact that once, like when you are training a data set, or when you are using a data set, you may need to transform that data set using one or more of data transformers, especially scalars. But one thing that you shouldn't forget is after predicting the value, after predicting, or after getting the prediction value, you need to go back to the original scaling. As you can see, the target scalar was using a standard scalar, and then just when we were fitting transform, the housing labels to frame, we were scaling them using the standard scalar. And then we used this scalar to train a linear regression model. Now the model is fit here, it's trained. And then once we have this data set trained, we created a new data set. Like this is, let's say, instead of here, suppose this is, let's say, this is a new data, and we wanted to predict this data using the model. This model is a linear regression model. Now we predicted, but the value that we are getting out of a prediction is a scaled prediction, and the way to go back to the original value, because in reality, whatever the model did inside should not be known to end users. End users give you values and they expect value in the proper scale. So this is how you go back to the scaling, and how you inverse transform. Whatever that we did fit transform, we have to inverse. The inverse transform remembers the value, right? The values, especially the standard deviation and the mean of the data set that it used to transform. To scale the original data. When we were scaling the original data, this standard scalar was using the mean and standard deviation of that particular column. And when we were inverse transforming, it has got those copies, the mean and standard deviation, and then it converts back to the original scale. Then the reality will not be missed. So this is an important point that you should be noting. Again here, transformed target regressor. And again, just you can have, instead of just remembering everything that we have done here, everything will be recalled. Now, transformer target regressor uses the transformer as a standard scalar internally. We are passing this internally, and this transformed target regressor uses internal, and then you can use whatever scalar that you need. And then we want to do a model fit for the housing median. Then just housing labels, right? We pass the housing labels data here for the housing median, and then fit it. And then just the prediction will be given. And as you can see, the prediction values. If I do here, then just you will get the exact same values without us doing predictions. I mean, going back and forth between the predictions. In some cases, you may not get this kind of transformed target regressor. You may not get that. You may have to do remember what type of regression that you used, what type of transformation that you used, so that you can go back in your transformation. Another is custom transformers. I think we should be enough. We should be done with this transformation process. You can write custom transforms, and I will move on to the k-means clustering. Any questions so far? Any question about transformers? Data transformation. In general, we discussed about transforming the data using we can transform data, categorical data using ordinal encoder and category and one-hot encoder. Numeric data can be transformed for one or another reason using different techniques such as min-max scalar or standard scalar or logarithmic natural logarithm transformation. So these are the three techniques. And in the process of transformation, once we transform, we shouldn't have to forget what we have done on the data, because at a later point, whatever we did on the transformation, the model remembers that. The model remembers, the model utilizes the transformed data and then gives you the transformed data. So you have to inverse transform the data back to its original state. So that's what we discussed here, especially here in this step. In this step, this is what we discussed. This is what we discussed. Transformation you can apply transformation, but the prediction value that you get out of the transformation, you have to inverse transform that. Otherwise, you will get a wrong message, a wrong value that doesn't represent the reality of the actual data set. The actual data, the original data set, reality gets changed once you transform portion of the data set. So whatever transformation technique that you used during the model training have to also be used post prediction. Now, linear regression is a supervised machine learning model. Then a supervised machine learning model, as a supervised machine learning model on a continuous data, it enables you to predict the value. Now it gives you the predicted value. It predicts. So these predicted values have to be transformed or inverse transformed back to their original value. That's the reason why we are doing that. And there is one question here: why it jumps over second order while it puts in ordinal mode? It gives values for 0, 1, 3, 4. I don't know what the question means. I can let you ask Kasaon. You can raise your hand and then I can let you ask. Raise your hand, Kasaon, and then I will let you speak. When you raise your hand, you will be at the top in the list. Otherwise, I can't find you in the list. Okay, good. Now I see you. Now you can unmute yourself and ask. Feel free to ask in Amharic. Unmute yourself and ask. I can't hear you if you are speaking. አይሰማኝም የምትጠይቀው እየጠየቅ ከሆነ እንትንህን ስፒከርህን አንሚዩት አድርገው። ስፒከሩ ላይ ሚዩት አንሚዩት ክሊክ አድርግ። አንሚዩት ራስህን ለማድረግ ኦኬ። መሪሁን you can go ahead and ask. ጥያቄ አለ? ጠይቅ። ድምፅህ ግን አይሰማም።
ኖ
እሺ እሺ ካሳሁን ጥያቄ አለህ? ጥያቄ አለህ ካሳሁን? ኦኬ የለህም። ጥያቄ ስላልገባኝ ነው የጠየቀው ካሳሁን። ራስህን አንሚዩት አድርግና ተናገር። ስፒከሩ ሚዩት ነው። ኦኬ I think why it jumps over second order while it puts in ordinal mode. Oh, okay. Now I got your question. It gives values for 0, 1, 3, and 4. The second value doesn't exist here. Okay, that's because it's because of the data set. The data set has every value in it, has every value in it, but yeah, so this, I think your question is 3011411030. These are only the 10 records. I can say, let's say 30, and if I say 30, probably just you would see 2 somewhere. Even not to here. Yeah, I don't see 2. Maybe we oh, okay, now I know. I will try on 50 values and then just see if we have 2 here. 2. We don't have 2 there, right? So what that means is, if you remember, like the counts somewhere. The counts. Where was it? Yeah, so let's change these to only 10. Only 10, and okay, let's see if, yeah, value counts. You see, so this has got only 2 values, and it's very difficult to find this value. Just like number 2 would be associated with, you see, number 2 would be associated with island, right? For island, we only have 2 records, and in the top 10 or top 100, we may not get that one of these 2 values. That's the reason why 2 would be associated with this particular value. And if we see in order, yeah, so 0, you see the order? 0, 1, and 2 is for island. But the total number of records in more than 7,000 records, we only have two values represented by the second index. So as a result of that, it's very difficult to find one of those values in here. Does that make sense? Yeah, good question. Okay, any other question? Any other question? Okay. We are almost done on this notebook. The next step is k-means. K-means basically this is about clustering, and we will cover clustering next week, clustering and pipelines, and I will be thinking to pipeline means whatever we do, we can put them in order. So pipelines are ways of organizing our data pre-processing, data transformation, everything in order so that everything gets executed one after the other without any issue, so that we can get our model trained at the end of the process. Maybe we'll consider select and train a model. So this is training and evaluating on the training set. Just we will be coming into a linear regression, and then pre-processing is a data pre-processing approach, and then just do the linear regression, and then the housing labels. Then it goes like this, right? It goes like this. The housing and using cross-validation, this is one technique among the list of things that we wanted to do is checking whether or not our prediction is correct. And so cross-validation means one way of checking whether or not our prediction did correctly. No, sorry. Cross-validation is a way of training a model by internally testing it in the process of the training process. And the cross-validation means the splitting your data set into multiple smaller sets, and then just most of the time like 10 small sets, and then just do the training process and ensure that the best model can be picked that basically represents. When you split the data into 10, 9 of them will be used for training and the 10s will be used for testing. So 10 times will be done. That's why we have 10 here. And we'll do that next week, fine tuning. So this is the 7th week. On the 8th week, I believe, now this is the 7th. On the 8th week, we will finish this and we will cover everything that we have on this. And on the 9th week, we will be able to summarize everything that we discussed in theoretical slides. I will present an entire slide set that basically covers everything that we discussed here on this end-to-end notebook. On this notebook, we have touched so many things, and we will be covering more. So everything will be covered in one shot using or a theoretical slide presentation. On that slide presentation is going to be a direct mapping of this, but organized in such a way that you know the end-to-end. And I'll be referring back the slide presentation details back to this Jupyter notebook. Any question? Any question? Do you have any question? Okay. ጥያቄ ካላችሁ ጠይቁ። If you have any question, feel free to ask. Otherwise, please rerun this notebook. It has got so many things in it, end to end, for machine learning, and then it gives you, just a good insight. And as I promised, I will be summarizing everything that we discussed. I'll be finishing it up next week and start summarizing everything, like the theoretical aspect of everything that we went through. Imagine the approach that I took is basically just showing you how to prove or how to generate the quadratic formula, right? How to generate the quadratic formula of a in mathematics, like just to find the hypotenuse of a right angle triangle, right? Or just to solve a quadratic equation. Sorry, to solve a quadratic equation, x is equal to minus b plus or minus whatever. And now, next, just on the 9th week, I'll be summarizing. And I know I will use the next few minutes to discuss about just whatever is remaining, but I will have to stop the recording for now. If there is any question, I will address before stopping the recording. Is linear regression is okay to model such numerous, huge valued housing data set in case it go through with simple data set? If the data set or variable becomes complex, is it fit to analyze or what else options? Yes, this is a very good question. A very good question. Yes. Is linear regression okay? Like linear regression is okay only if the relationship, if just your data follows a linear approach, right? A linear approach. And if you remember, we saw that the housing median value follows a certain linear paths, like just in the graph. That was the reason why linear regression came into picture here. In the graph, let me go back, and the housing median value followed a certain linear path in our graphing. So somewhere you see here. So here the median income and the median house value were following a certain linear path. So this is the reason why linear regression was in use here. But if your data doesn't show a linear distribution in a scattered plot, linear regression is not advisable to use, because linear regression is only for linear data representation, right? For linear, for data sets which follow a linear distribution. there are other algorithms that you could use for predicting values, and it depends on the data. And just we haven't completely seen what kind of for example, like just at times when linear regression doesn't help you get the data, you would have to use logistic regression, right? Or a sigmoid logit. And it depends on the type of data. For this data set, linear regression may be applicable for only for some of the attributes, not for the entire data set. So that's a very good question. That's a very good question. You cannot simply apply just a multivariate regression. Also is another thing that you may consider, but provided that you can minimize the error in the prediction process. But and you obviously just you will learn, you will see you cannot reduce the error any further in the prediction of whatever linear be it multi-variate linear regression or just a simple linear regression, not properly predicting the values. Okay, any other question? Okay. Perfect. Okay. Thank you. Let me stop here and then just I think I remember last week there was